Utilitech is provide security consulting services for different organizations, primarily those that have control systems in them. So any organization that has some type of a computer system that's controlling devices in the outside world. So like energy sector, electric utilities that have computers that are controlling the power grid, oil, water, and gas that has different types of control systems controlling the resources going across the pipelines, manufacturing that are building things with robotics and machinery. Basically anything that has computers controlling something in the outside world that's making a change in the outside world. And that's what we specialize in at Utilitech, is trying to help these organizations build secure architectures, deploy these securely, help them do assessments to find vulnerabilities, and do penetration testing to try to see what an attacker can do if an attacker were to get to the control systems themselves. So I've been in the security field now for about 13 years, and about the last 5 years have been focused on the control systems themselves. Before then, I've done a lot of other defensive to security, a lot of penetration testing in the web, in embedded hardware, and what we're going to be discussing today is RF communications. So when we are working on different types of technologies, especially control systems, it's very common to have a control system that has what we call a sensor network. They have multiple different devices that have been spread around that have some type of a sensor that's taking a reading from the real world. Either some type of a voltage or some type of a GPS signal, some type of a temperature. Okay, so we have lots of different sources providing information back to us. And often, these wireless sensor networks are going to be using RF communications to send this information back. So one of the things we do at Utilitech is we work with these sensor networks that have these RF communications to try to help the vendors and the manufacturers creating these devices understand what vulnerabilities might be present inside of these devices. So that's what I'm going to talk about today, is to try to give you guys some insight on how to do RF testing. Because RF testing, without somebody to introduce it to you, can be very difficult to try to learn on yourself. But once you have somebody teach you some basics, then it makes things much easier to get going inside of RF communications. Oops, wrong button. Okay. Now, when I work on control systems, that's something that's often very hard to try for normal people to try to get their hands on. However, all of us have plenty of different types of wireless devices that are around us that we can actually use to do our testing and to learn how to work with RF communications. And if you are working for a security team that is working in normal IT security, many of these organizations that you might work for still have many different types of control-like systems that are being used inside of your infrastructure. Things like the fire alarm systems. Often in large organizations and large buildings, if you have one single fire alarm that goes off, that fire alarm will often set off alarms on all the other devices that are there. Sometimes that's via some type of a wire that's communicating back and forth and ties all the fire alarms together. Sometimes it's going to be some type of a wireless communication that goes back and forth between those alarm cards. Another example is proximity cards. So many of us may have some type of a card that allows us to open doors for our facility, or in certain situations, especially common in medical practices, how a doctor or a nurse can wear some card on their belt, and then when they walk up to a terminal, as long as they're by the terminal, it automatically logs them in, and then when they walk away, it automatically logs them out, which is a good thing for security. But this is a wireless communications that we can actually try to attack and try to take advantage of. There's automotive gates, so if you come up to a building that has a large gate to be able to get drivers in, sometimes there will be some type of a wireless button that the driver can push to open the gate. That's something that can also be captured and try to be attacked. We have inventory control systems if you work for a large warehouse. It's very common for modern inventory systems to start using some type of a wireless communications to be able to get a very quick count for how many different pallets they have and where each pallet is located inside of the warehouse. Car alarms are another good example. If you have a car alarm, you have some way to turn the car alarm on and off, or to be able to start the car remotely. Conference rooms, we often will use wireless devices inside of conference rooms, whether it's going to be something like this to be able to forward the slides, or it might be something like this microphone that I'm wearing. Okay, that's actually transmitting via RF communications back to the location to be able to do the recording. Okay, all of this also is something that we can actually capture in the air and be able to inject or spoof or to change inside of the communications. Hospital beds are another one that's very interesting. If you've ever been to a hospital and you had a broken leg or some type of a surgery, you know the last thing you ever want to do is to move. Well, sometimes our hospital beds are going to be wireless communications where they'll have a remote and you can move the bed up and down. And if an attacker wanted to do something very cruel to somebody, you could get in and start changing all the beds and moving the beds on the patients that had just had surgery or in critical conditions. And then finally, building automation systems. Different types of systems inside of buildings that might turn the lights on or off during certain parts of the day, or be able to control the temperatures inside of the rooms. Sometimes these systems also have wireless communications. So all of these are types of control systems. They're not the same type of control systems that we usually call SCADA devices or SCADA systems, but they're all kind of a lightweight or a simplistic version of a control system that we have that all of us will be able to interface at sometime inside of our careers. So really it's just up to you to be able to look around to try to identify what types of systems that are actually there and what types of communications they use, if they're using wireless or some other types of form of communications. So one thing that I've done with Utilisec is I've worked on many different types of projects for the Department of Energy in the United States and different utilities and community groups, trying to provide guidance to different types of control system providers, as well as what we call asset owners, organizations that actually buy these control systems and deploy these control systems like electric utilities, oil, water, or gas. One of the guidance documents that I created was called the NESCOR Guide to Penetration Testing. And this is a methodology that we created inside of this document that describes what can we do, or how can we actually perform a penetration test. So what are the overall steps and the overall tasks? Now this guide is publicly available. You can go and download this online. It's very easy to find. Just search for NESCOR Guide to Penetration Testing. And you'll be able to find this full document that goes through and talks about this methodology, and not just the methodology, but it goes through the individual tasks. So this document actually contains 56 different penetration testing tasks that make up this methodology. So if I'm going to do a penetration test, I can start with working on doing a penetration test of the server operating system, or after that, then I can work on the different types of user interfaces that are exposed inside of the system. Then I can work on the different control system protocols that might be communicating back and forth across the network connections. And then finally, I can work on the embedded devices themselves. Now for RF communications, that's going to be a form of network communications. So when we're working on network communications, not only are we going to try to capture data with Wireshark and TCP dump to be able to analyze the communications, but we can also use specialized devices like the software-defined radio to be able to capture the communications in the air to see if we can then extract the data back out of it. So it's very similar to working with Wi-Fi. If any of you ever have worked with any of the Wi-Fi based tools to be able to capture capture data out of the air. Kismet's probably one of my favorite for Wi-Fi to use. And there's other tools like the Ubertooth that you can use to be able to capture Bluetooth. But if you're not using Bluetooth and you're not using Wi-Fi and you're using some type of proprietary communications, something like this audio mic, what you're going to have to do is you have to use some specialized equipment and be able to tune it to the right frequency to be able to capture that information. So all of this is very possible. Now, in order to do this, not only do you have to have some hardware tools, you have to have some software tools to help do this assessment. When I created this NESCOR Guide to Penetration Testing and help people understand how to do penetration testing for control systems, one of the questions that they asked very, very soon after I released this document is, well, now you've told us how to do a penetration test, you've told us the task to perform, but where are the tools? What tools do we use? And sometimes we can use the normal tools we use in penetration testing, but often we're also using specialized tools that are special to the control systems or special to hardware hacking or RF hacking. So, and there wasn't a lot of good distributions out there that talked about RF or hardware hacking. So I put together, about a year ago, a new distribution called Samurai STFU, or the Security Testing Framework for Utilities. And this is a distribution like Backtrack or like Kali Linux that is a virtual machine that you can boot up inside of your laptop that has all the different types of control system protocols, the hardware hacking, the RF hacking tools that are pre-installed and pre-configured. It's not like Backtrack or Kali that tries to have every single tool in the world in the one single distribution. This distribution tries to have just the best tools for web pen testing, the best tools for hardware pen testing, the best tools for RF pen testing, really focusing on the tools that we need and that we always use to be able to do our jobs. This distribution also goes through and doesn't just provide the tools, but we try to provide a lot of documentation and information for organizations and individuals to help them perform these penetration tests. So we have documents that describe the methodology for us to be able to follow. We have documents that will go through and describe some of the network protocols that are available in the control system world. Because many people, the first time you ever see a SCADA system, the protocols are completely different. People if you haven't been around SCADA, you've never seen the SCADA protocols, and there's many types of SCADA protocols. So we have packet captures of different SCADA protocols, so you have a sample to be able to see what those protocols look like. We also have different types of simulation devices as well in the distribution. So if you want to be able to learn how to communicate using the SCADA protocols, we have some simulated devices that you can communicate and talk with to be able to learn how to generate your own SCADA protocols and be able to fuzz the SCADA protocols and be able to perform man-in-the-middle attacks to the SCADA protocols. Okay, so that was really the goal of the distribution, is to provide a tool for all the different utilities that are out there. Any organization that's an asset owner that owns critical infrastructure or owns control system, give them a tool to be able to do penetration testing and do security assessments of their infrastructures. But it's also to really help anybody in the security community be able to learn more about these control systems. Because right now, for people that have experience to do penetration testing in the control systems is a very, very small number. And the number of asset owners that need people to perform penetration tests is very, very large. So we need to start disseminating and helping other people learn this knowledge and learn these skill sets so that we can adequately start testing these infrastructures and start trying to find the vulnerabilities and get rid of them. And not just testing, but the most important thing is testing in a very safe and secure way. Because if you go through and do your normal IT penetration testing techniques on a control system, it's very likely to crash the control system or even in some cases brick or ruin some of the devices. So there's some very important things to learn about how to do a penetration test, when to do it, and what are the safe ways to do it inside of a control system that we're trying to disseminate and help people understand through the distribution, as well as classes like we taught here at Black Hat, or sorry, at NOLCON and other conferences like Black Hat and the SANS Institute. Now specifically for RF communications, here's the individual tasks that we use for doing penetration testing of RF communications. So if you find a device and you want to talk the RF communications, here's the overall steps. The first thing we're going to want to do is we want to go through and use something to capture the RF signal. We want to capture that signal so we have that information available to us, that we can start working with it and then processing it at a later time. We also want to go through and do a spread spectrum analysis to be able to identify what types of data or what types of encoding might be used for that communication. After that, we want to demodulate the data because all the data when you communicate over RF has to be modulated or have that data put on some type of a carrier wave for communications. We have to find a way to extract that data off that carrier wave, which is called demodulation. And then after we demodulate, we end up with what we call a bit stream. It's basically a serial streams of ones and zeros. It's our packets are in there, but we don't know where the packets begin, we don't know where the packets end. It's just a whole bunch of ones and zeros. In fact, we don't even know where the bytes begin and the bytes end. We just have a whole bunch of binary ones and zeros. We need to figure out, okay, well, this is the single binary bit where this very first byte starts to be able to get it. So that takes a lot of time to be able to take it from a bit stream back to a packet. And then after we do that, then we can go through and start performing other types of attacks. Maybe like a replay attack, where we take the signal that we capture and we simply replay that signal to see if we can do replay attacks. Or find some way to generate our own traffic and then transmit our own traffic to be able to spoof or to try to perform some type of a man-in-the-middle attack on that RF communications. So the very first step is being able to capture that signal. And this does sometimes take a little bit of effort. It all depends on the signal that you're working with. Some signals that are very, very chatty signals that broadcast a lot of RF communications are very easy to find. For instance, this wireless mic I'm wearing. As I'm speaking, it transmits a lot of data. And so it's very easy, if I was to look at the frequency and try to find it, it's very easy to find because you can see the data flowing very, very frequently. But on a sensor network, sometimes these sensor networks only send 2 or 3 packets every 5 minutes. and those are very difficult to find. So in those situations, we usually try to talk to the control server and send information to the sensors to make them speak more so that we can actually find them inside of the communications. Doing things like a firmware update that forces them to be able to generate a lot more traffic so we can find the signal. Now, when we want to capture this information, there's two main ways that we can actually capture this information. If this is a proprietary or a less common form of RF communications, there's not, you just can't go to the computer store and go buy a special card, an RF card for that communication protocol. It's not like Wi-Fi or Bluetooth. We have to use something special to capture that. So the two choices are a software-defined radio, which is what this is. In fact, in reality, what this is actually a TV tuner card for watching TV in Europe. It just happens to be that the architecture of how they built the electronics is the same as a software-defined radio, at least for receiving, and the open source community built a driver for it so that we can use this as software-defined radio. So this makes it very cheap. Before we had these, which we've only had for 2 or 3 years now, before we had these, the cheapest device that we usually had was a USRP-1 that was about $1,000 US. So it was very expensive to do RF communication testing. Now, $20, $20 US to be able to capture the signals. It cannot broadcast, but at least it can capture, okay, which is important for what we're trying to do. So we have a couple different options for hardware if you want software-defined radios. This is capture only. The HackRF and the USRP2 are other devices that we can use that can receive and they can transmit, but they are more expensive to be able to do it, to use them. Now the benefits of the software-defined radio is it's very flexible because with this hardware, it acts like a sound card. It basically captures any type of RF communication that's coming in. I just basically tune it to a specific frequency and it will capture it for me. And when it captures it raw and it saves it to a file, very similar to a WAV file format. It is different, but it's similar how it just captures all that information and just saves that information onto a file. And then we can save that information and then process it later to try to do the demodulation and extract the information back out of it. So it works very easy because of that flexibility. It also has some great open source tools available called GNU Radio and GNU Radio Companion that allow us to be able to control this device and very quickly build schemes to be able to pull down that information that's needed. Now the disadvantages of software-defined radio is because it's so flexible and because it has so many different options, it's just doing a raw acquisition, and then the GNU Radio software allows us to do any number of modulations, demodulations, and actions on it. The GNU Radio software is very, very complex. And the user interface is very logical once we get to use it, but initially it's kind of very strange to use. So that's kind of the downside, is it is very easy to get lost in the complexity. It's not quite as simple to use. The other thing about GNU Radio is because all it's doing is just a raw acquisition of the RF signals, when you go to process that data, it's doing it all via software. So it's very, very taxing on your processor and your computer to be able to do it. Because of that, it doesn't have to do it real time. We can, since we're doing it out of signal, we capture it first, we can actually slow the process down. And wow, right in the middle, huh?
You wanted to screw your talk.
Pull the Velcro.
Thank you. Exposed. Chill, enjoy.
Bye. So, the other option is RFCat. So RFCat's a newer project that's only been out for maybe 2 years now. RFCat uses a different piece of hardware. It doesn't use a software-defined radio. It uses another type of a device that has an RF chip that's built into it. And the difference is, this is the same type of RF chip that would be used in the control system. In fact, most often, if you're pen testing a control system or trying to capture it, quite often this is the same exact RF chip that you're actually working with. I use a lot of smart meters in the work that I do to do testing, and this is the same chip that's in a lot of the smart meters that I'm testing. So what we're doing here different, though, is most of the time when you have an RF circuit, the electrical engineer will actually hard code that RF signal inside of it, how to communicate the RF signal. What we've done here with RFCat is Atlas and Don Weber, who are the project leads of RFCat, they've gone through and they've rewritten a firmware for this device that lets you configure this device on the fly. So you use the RFCAT tool, you tell it what frequency and what type of modulation to use, and it will go and reconfigure this card, so that way it's still doing all the work via hardware, so it's not very hard on the computer, but then you still have the flexibility to be able to constantly change it as needed to be able to get this to use what you want to do. So they named it RFCAT. It's after NetCat, if you ever use NetCat, a generic tool to generate data on a network. Well, this is a generic tool that lets you generate or receive data on an RF network. So a wonderful, excellent project. The hardware is a lot less expensive because the hardware is just the same inexpensive chips that we're using in the other devices. So usually it's below $50 for any of the hardware to do this. The downside is you are going to have to reflash it. They have a custom firmware, so you are going to have to get a special programmer to go in and reflash the microcontroller on the device to have the new firmware that's on it. The nice thing, however, about this is because it's very inexpensive, but it's also very easy and straightforward. The RFCAT software basically gives you all the functionality that this chip provides for modulation and demodulation of frequency ranges. So you just have to basically tell RFCAT what you want it to do, and it will configure this device. So it's very, very straightforward and easy to use. In fact, it has some advanced features, like it has a frequency hopping recovering algorithm. So if there's something using frequency hopping, if this can receive enough samples of the data set, it'll actually try to automatically recover the algorithm so it can start following the algorithm. So a great, great tool that they have. Now the question is how do we actually find that right frequency? Sometimes that can be difficult. When we are going through, when we're trying to find the RF signal, be able to capture, we sometimes don't know where to look. And we have to try to look around for that signal. But often, if we're doing a formal penetration test, usually you'll start off a penetration test with some type of an architecture review, where you'll sit down with the engineers, you'll sit down with the architects, you'll sit down with the vendors, and discuss about what the product is and what type of features the product has. Finding the frequency is actually the easiest thing you can do if you have access to the documentations or if you have access to any of the architects or engineers. Because by law, in every single country in the world, the manufacturers must advertise what frequency their devices are using. So it's very easy to find this information. You can also usually go to any number of the different regulatory bodies around the world, depending on where this device is sold. And most of the devices that are being sold commercially have to be registered with the regulatory body for each of the major countries that require it. The two biggest ones that are out there is the FCC in the United States and the European Union's registration database. And you can go out to those databases and request, give them the ID that you're looking for, and which are always labeled on the device. Once you find that ID, then you can go and recover the documentation for it that we're registered with, which will always have the frequency as well. In fact, they'll have a graph usually of exactly where that frequency was and what that frequency actually looked like when they were doing the testing of that to get the certification. So that's a very good place to look for it. You can also go through and look for patents as well. If the control system has some type of a patent around it, like many of them do, often the patent will talk about the RF communications part of the communications. So sometimes you can get information from the patent filings. And then finally, if you don't have any documentation, you just have this device and you can't find an FCC ID, or the FCC ID doesn't work inside the database for some strange reason, which is fairly rare. Then what you can do is you can sit there and go through and look through what we call the ISM bands, or the industrial, science, and medical bands. These are different frequencies that have been set aside for devices that don't have to buy special licenses for communication. Most of the RF communication devices that we purchase are usually broadcasting and communicating somewhere in the ISM band. Okay, now there's several different ISM bands. Here's the master list for the ISM bands that are being used around the world. Okay, ITU is the organization, the standards body that's gone through and set aside these different ISM bands and frequency ranges, and then each country around the world has to choose to whether to accept or reject ITU's recommendations. So ITU and their recommendations for what we call, if you look right here on the center frequency, this is what they usually call the band that's there. So for 433, okay, this is the frequency they've set aside for all of Europe, Africa, Middle East, Russia, and Mongolia. Okay, but most countries around the world also accept that frequency as well. Then we get down to the 868 range. Now what this is this technically isn't an ISM band. This is what we actually call an SRD band for research. However, in Europe and here in India, it's a very common frequency that they actually use. So if you're doing RF testing, you're going to want to be looking at this 869 band. And once again, center frequency is where it is. This band is actually 2 megahertz wide, so it actually starts 868 and goes to 870 is the range that you'll actually have. In the United States, the most common one that we have in the United States that's being used is the 915 megahertz range. And 915 actually has 26 megahertz width, so it starts at 902 megahertz and goes all the way up to 928 megahertz. So that's the range that it's actually using. And you'll also see that we have Wi-Fi here as well. So Wi-Fi is also part of the ISM band, so Wi-Fi, Bluetooth, Zigbee on the 2.4 gigahertz range, so which is 2.4 to 2.5. And then if you have more of the newer Wi-Fi, of course, you can get up into the 5 gigahertz range as well. So if you don't know where it is, you can simply start going through and searching through these bands to see if you can see the signal. Okay, so that's another option that you do have. Once you've actually found the signal, then what you're going to want to do is you're going to want to go through and try to see if there's some type of a spread spectrum analysis, or some way that they're actually encoding that information. In fact, let me go ahead and get this device up and running. What I want to do is I want to do a live demonstration, because live demonstrations are always good for an audience, right? Especially when you're on film, because they always work.
Did he say a phrase to the demigods?
No, but I went scuba diving this morning, so. Okay. So this is Samurai STFU, the distribution that I spoke about earlier. Okay, and what I'm going to do is I'm going to see if I can see all my devices here. Okay, so here I have my Texas Instruments. So what this is the smaller one. This is actually going to be an access point for the RF communication that I want to speak. And this is actually going to be using the 915 megahertz.
Can you increase the phone?
No.
You can't see.
Yes, of course I can. Thank you. Okay, so this Texas Instruments is going to be the access point, or the one that's communicating the wireless communications. The other device on the other end of it is actually going to be this little watch. This watch happens to use one of the Texas Instruments CC1111, which is the same exact chip that's used in a lot of these control systems, the same chip that's used in a lot of the meters that I do testing on. And so what we're going to do is we're going to have this watch actually communicate to the access point, just like it was a control system. And technically it kind of is. It actually has capabilities of sending a three-way access. So like a robotic arm is the exact position it is. That sends that information back, and we'll see that. It also can send temperature or the voltage level of the battery as well. So very similar to a wireless sensor. So we're going to go ahead and do this, set this up for that communications. The other device here, which is the Realtek semiconductor, this is my software-defined radio. So I've just verified that they're both visible. I can see them inside of my virtual machine. So I'm going to go ahead and start this communication. So sudo Kronos Control Center. Okay, so here's my control center. I'm going to start my access point. I'm going to start my watch. Okay, so now you can actually see that this watch is arranged. So if I move the watch, you can see it controlling or sending the information back to my computer. So I do have wireless communications going back and forth. And also, if I hold my watch still, I still have data going back and forth. Look at the numbers at the very bottom. So I don't even have to move the watch. The communication's always going. It's not just sending data when I'm moving the watch, but it sends data all the time. So I don't even have to hold the watch. So I'll go ahead and I'll just put the watch down, since it is still communicating and sending the data. Okay, so now I have my communication going. What I want to do is I want to see if I can find that communication to be able to talk to that communication. So the tool that I'm going to use for that is called GNU Radio Companion. So GNU Radio Companion. Okay, and this is the communication that I'm going to be using. So what I'm doing here is I've pre-configured this for the demonstration, so I have to build this by hand. But let me at least show you what's going on here. So what I have is I have this Osmo SDR source. This represents the driver of this card that I have in the software-defined radio. That represents that card. Okay, it takes that card, this driver has that card configured to go through and look at 905.99 megahertz. So that's the frequency it's going to lock onto for this card. And it's going to take this and actually capture 1 meg worth of samples to send back, 1 million samples per second, to send back to my GNU radio for processing. So once it grabs this, it's going to send all this information over to what we call a low-pass filter. Okay, this low-pass filter, in fact, yeah, I better leave it like that. It's going to take this information over to the low-pass filter. Once I tune it in, here, let me do this. This is actually part of the next step. Instead, I'm going to come here. I'm going to destroy that link. Connect this link. Destroy this link. Okay. Well, it's not going to like that. Disable. Okay, disabled the circuit that I don't need. So all I'm going to do is I'm going to capture it with this source, and I'm going to send it over here to what we call the GUI FFT sync. This basically is my spectrum analyzer. Okay, so with literally open the program and you add 2 blocks to it, I have a spectrum analyzer built. Okay, so let me go ahead and start this. Okay, so this is my spectrum analyzer. And right here with this range, I can go all the way down to 902 or I can go all the way up to 928. So I have that full ISM band in the 915 range. And what I want to do is I want to basically just keep on going back and forth until I can find that signal going that's jumping up. And so already being familiar with this watch, I know this watch is over here at 905.998. And in order to help you see it, I'm going to go ahead and tell it to, let's do a peak hold. In fact, I probably need a larger, it's not updating fast enough, so I'm not seeing it. So what this is I can see a little bit of a signal here. See how it's kind of jumping up a little bit? I see more of a signal, and you kind of look for this square signal that's there. In fact, if I try to zoom in on this a little bit. There we go. Okay, so I can see that signal now that's actually being captured here. So I can see that data going back and forth. So I've been able to see that communication. So this is that spectrum analyzer. I'm finding that signal. I found the signal. I can start acquiring that signal. Now, with a little bit of research, I can try to see if it's using something like frequency hopping or spectrum analysis, which all the vendors are going to have to announce. If they're using frequency hopping, they're usually going to be very proud of that, and they'll announce they're using frequency hopping. In fact, from a regulatory perspective, if they use frequency hopping, they can broadcast at a stronger signal rate. So therefore, they're almost always going to advertise the fact that it's using frequency, so they can say, yes, we have a stronger signal. Now, if you ever have to recover that algorithm, that's actually a fairly difficult thing to do. It's very, very time consuming. In fact, some people think that because it's so difficult that it's a good security mechanism, that it's equivalent to encryption, but it's not. And the reason why is because that algorithm, once it's known, can be thrown into a script and posted online, and anybody can actually have access to it. So it's not like cryptography that has changing and rotating keys. It's something that is kind of a layer of obscurity, but once it's recovered, then it's a very bad thing. So it's not a good form of security inside of these systems. But you can go through and we can try to recover it. We can grab it from the RF chip if we can get it to the RF chip. We can try to extract it out of the firmware if you can reverse engineer the firmware. Or sometimes you can capture it by doing bus snooping on the board. If I take the device apart and try to capture the communications between the microcontroller and the RF chip, sometimes you can see the microcontroller telling the RF chip, hey, jump now, jump to this frequency, jump to this frequency, jump to this frequency. And sometimes you can recover it that way. In fact, if you want a really good presentation, I have a URL here at the very bottom of the screen about how to use bus snooping and capture it. This is a presentation that was done by Atlas. He's one of the guys that did RF Cat. this is a presentation of how he's actually gone through and recovered the frequency hopping algorithm by doing bus snooping on some of the electronics. So it's a very, very good presentation, I recommend. So once we have the signal, if there's no frequency hopping, or if we found some way around the frequency hopping to get rid of it, the next step is to do demodulation, to try to extract that data off that signal. So when we have a signal, we're always going to have some type of a baseband carrier wave that's transmitting the data. And we'll have data that's actually encoded on top of that carrier wave. Now, it can be encoded either via an AM modulation, okay, or what we call an amplitude modulation, or a frequency modulation. So everybody should be familiar with AM and FM, right? The radio? Well, that's the big difference, is how they're encoding the data on the signal. And each one of these is actually an entire family of different types of modulation. So AM is a whole family of modulation types. FM is a whole family of modulation types. So the difference is, if I want to encode data onto the carrier wave with amplitude modulation, in order to encode a 1, I'm going to have a stronger signal. In order to encode a 0, I'm going to do a lesser signal. Okay? So I'm actually playing with the amplitude of it, but the frequency stays the same the whole time. Now with frequency modulation, it's different. In frequency modulation, we actually keep the amplitude the same the whole time. That's why FM sounds better. AM kind of louder and quiet sometimes when you start getting bad signals. With FM, it's generally good quality or not, but it doesn't, it's more consistent. Because what they're doing with FM is they'll have the same carrier wave, they'll choose a specific frequency for the carrier wave, but if I want to encode a 1, I might speed that frequency up just a little bit. Or if I want to encode a 0, I'll slow the frequency down a little bit. So it's basically changing the frequency, but it's always centering around that center band frequency. So once you tune your radio to that center frequency, it just looks, okay, it's a little faster, it's a little slower, to be able to figure out what type of data is being sent. Now when we have modulation, there's two different types of modulation. There's an analog modulation type, and there's a digital modulation type, depending on what type of data you send. So right now, this wireless mic that I'm using, this is using an analog modulation type. It's taking my voice and sending it through an analog signal back to the base station for recording. That's something that we can play with, we can capture, we can replay with, but for penetration testing, it's kind of less interesting to us. We're usually more interested to the data, or to the digital communications, and the digital modulation types. So if I'm going to be playing with something like this watch, that is broadcasting communications, this is going to be a digital signal that's being sent, so it's going to be using one of these types of modulations. So the goal is to figure out what type of modulation it's using, so then I can try to demodulate and extract that data back off. In order to find the modulation type, what we usually do is, once again, go back to the documentation, go back to the engineers, go back to the architects, and ask, what type of modulation type are you using? Read through the documentation. Does the documentation talk about modulation types? Most of the time, public documentation that's posted on websites usually does not specify the modulation type. I've seen it a few times, but it's been more because the marketing team that built the documentation, they got details from the engineer and they basically copied and pasted the modulation type in on accident to the marketing documents, to the marketing specs. So the easiest way to find modulation types is look in the documentation to where it mentions the frequency, and usually right next to the frequency, if you see a 3 or a 4-letter acronym, that's usually the modulation type. Okay? So if you can find it there, it's very, very good. Or if you can get somebody to tell you, one of the engineers or architects. If you can't do that, then go look at the regulatory databases. Find the FCC ID that's on the device. Go back to the regulatory database and download the documentation that they have there. Okay? When you get the documentation and it talks about how they perform the testing and it tells you which frequency they're using, they will almost always tell you the modulation type that they're using as well. So that's a very good thing to have. Once you know the documentation, when you see the modulation type, then we just program that into GNU Radio, and it will do the hard work for us. Now, for this, unfortunately, this is not sold commercially. This is a developer's kit. Any of you guys can request this from TI and get a copy of this watch. It's about $60 US to get one of these, and it comes with the access point for communication. So it's a great, fun thing to play with. In fact, the firmware is also open source on it. So you can actually reprogram the firmware to have all sorts of fun with your watch. However, for the frequency and for the modulation type, they don't mention that. They mention the frequency. When you buy it, it says it's a 915 or an 886, depending on or 868, depending on which version you buy, the European or the US one. But that's all they say. They don't tell you modulation type. Even in a detailed documentation from TI, they never mention the modulation type. And I through many, many pages trying to find it. So what I did instead for this device is I resorted to the source code. It was open source firmware, so I went and looked in the source code repository and found a great comment section that describes exactly how the radio was configured. Okay, and if you look further down below the comments, you'll actually see it in the C programming code of how they were actually configuring the radio. But this is much more human readable, so it makes a better screenshot. So here I can actually see that the frequency that this device is communicating is 905.998. Okay, and I can see that the modulation type is GFSK. So all I have to do is use this information to go back to GNU Radio Companion to program that into GNU Radio Companion to be able to extract the data back off this signal. So here's my great signal. I can see that communication going back and forth, so I am capturing some information here. What I'm going to do is I'm going to go ahead and stop this. I'm going to re-enable this. Can't I do both? I guess not. Okay. Then I'm going to take this link, destroy it, hook it out here. Okay, so basically I've just reconfigured this. So here's my source. It's going to send my data over to what we call a low-pass filter. So it's already tuned to the right frequency. It's going to send that signal over to a low-pass filter. And you saw on the graph, you saw that great little spike, but on the side we had a lot of noise on the sides. So a low-pass filter is going to take all that noise on the sides and cut it off. So when I look at the configurations, it says that this low-pass filter is using a cutoff frequency of 150 kilohertz. So it takes whatever frequency I'm tuned to, and I'm tuned to 905.998. It's going to go 150 kilohertz above that signal and 150 hertz below that signal and start cutting off all the data. And then what it has is what we call a transition width, which means as it starts cutting off the data, it's not going to just cut it off straight. Instead, what it's going to do is it's going to transition and slope it off over a 100 kilohertz range outside of that. So by the time we get 250 kilohertz off, we should have nothing. Everything should be filtered out. Okay, but within the first 150, we have all the data. The last 100 is kind of sloped off and kind of tuned down a little bit. Okay, after that low-pass filter, we take the output of the low-pass filter and we send it to two locations. We send it back to my FFT sync, that spectrum analyzer, so I can see what the signal looks like. So you'll be able to see what the low-pass filter did. It also takes it over to our GFSK demodulation object. So this allows it to take that signal and demodulate to extract the data back out. Okay, once I actually have the data extracted back out of the demodulator, it's going to send it over to a file sync so that I can see all that binary data being stored in a single file. I can go back and extract and try to play with that data. Now once again, this file sync, it's going to have the raw bit stream that's coming back out of the device. But it's just that, it's a raw bit stream. I don't know where packets begin, I don't know where packets end, I don't even know where bytes begin and bytes end. It's just a whole bunch of ones and zeros. And so once I get it here, then I still have a lot of processing down the road to be able to extract that information out. And that's where a lot of the reverse engineering comes into play, is trying to figure out what you actually have. So I have this object built. Let me go ahead and, oh, no wonder why I had it bad. I was wondering why I didn't have a very strong signal. It usually helps if you plug in the antenna. For some reason, antennas make RF signals better. Okay, so we can still see here, I still have my watch connected, still communicating. I'm coming here, I'm going to tell it to re-execute this flow. Okay, so now I can see that frequency that I have, this is my signal, and now I can see that it's all cut off. That's what that low-pass filter did. It got rid of all the noise on the side. So I have a nice, clean signal that I'm focused and tuned into. If you want to see what that looks like, I can say I want to do a peak hold. And if you let it sit here for a minute, you'll see this very, very stereotypical signal. Okay, often you'll see some type of what looks kind of like a castle, and it's fairly symmetrical back and forth of what the signal looks like. You usually see some spikes right in the very middle. Okay, so that's my center frequency that I'm tuned to. Okay, so once I have that frequency, because I told it to run it through the GFSK demodulator and save as a file, it's saving as a file right now. So I can actually open up. Let me go ahead and stop this because otherwise the file grows very, very quickly. Come back over here. Can't type today. Okay, so that's that created, told it to use. Oops, let's do the Chronos. Okay, so I can see right here that this file is 43 MIGs, so it actually did gather quite a bit of time in just a few seconds that I actually had, so it was generating a bit stream there. So it's good that I see data inside of it. Now, let me show you what this looks like. Now this is literally a bit stream, so it's a binary type file. In fact, when in doubt, remember just use file to figure out what it is. So file, Chronos, you say, hey, it's just raw data. So we have to use something, we can't use less, we have to use something like XXD, we had some type of hex dump tool. Okay, so this is my file. In fact, hi. Let's see, hold on. Stop. Are you done yet? Helps to pipe it into us. There we go. Okay, so here you can actually see that we have a whole bunch of ones and zeros. In fact, for you, those of you guys that have done a lot of work with binary files, either with doing shellcode and exploit dev and malware analysis, you can see here in a hex dump file format, it looks very strange, the fact that your hex values are not hex values, they're ones and zeros. This is something you don't usually see. Okay, what this is this is literally a format that is a byte encoded bits. Okay, so I have one single bit, a 1 or a 0, that's represented by one whole byte. And part of the reason why they did this, it's a huge waste of space, but part of the reason why they did this is they want you to remember that you don't know where the beginning of each byte starts. Okay, it's up to you to figure out where each of those bytes actually begins. If it tried to use it in a more efficient format, it might have all of its bytes misaligned, so it means nothing to you. So they left in this format up to you to try to figure out where it begins and where it doesn't begin. And as I look through this, what you want to do is you want to look for more patterns just to make sure I have something meaningful. If I see random data, it means that you probably didn't get anything good. But if I look at this, I can see very quickly that it's not random. I have a whole bunch of ones and zeros, and I have a whole bunch of zeros representing. And I have that consistency going back and forth. It just doesn't look random at all. Okay, so that's a very, very good sign for us to be able to see that we have something that's looks like good data. And then from here, it's really up to you to go through and try to see what other type of information you have available inside of this capture and try to reverse engineer There we go. Okay, to be able to take that bit stream and figure out how to get it back into packets. Often, unless you have access to the actual source code to see exactly how things start, or if you have access to the engineer to be able to find out exactly what he's using for the access key, which tells it, when an access key is a certain sequence of bits that tells it, okay, here's the beginning of a signal. If you can figure out what the access key is, then great. There are some common access keys that you can look for. If you do a little bit of research online with Google, you can find about some of these common access keys and see if it's being represented in the data set to see if you can find out where the packets are beginning and where the packets are ending. But other than that, if you don't see that, then it's up to you to do that reverse engineering, send known signals, to be able to try to correlate with what you sent to see if you can recover that information. So, and then after you do that, if you're doing the penetration testing methodology, it really comes back to what do you want to use, what do you want to test, how do you want to try to exploit the system. You can try transmitting. The most easy thing you can do for transmission is doing replay. I can take my raw capture back to a file and simply run that in reverse back through my schema to be able to rebroadcast that back out to the world. So I can see if I can replay a signal. Like for instance, one thing that we'll often try to do is on some of the control systems, something that might turn off power or turn power back on with a wireless signal. I'll capture a wireless signal that's turning the device off. And then after I've caught it, I'll turn the device back on, and then I'll come back and I'll try to replay that turn off signal and see if I can actually replay the signal, replay the control signal, to see if they have replay protection turned on or not. Okay. So that's basically what we're doing with these devices. But that's pretty much it for the presentation. We have about 5 minutes left to be able to answer any questions. If we don't have enough time to get to your question, please feel free to use my contact information. I do have my email address, both my personal and my work. I have Twitter link on there. I have my cell phone on there if you need to get in contact with me. And also you can find me on Facebook, you can find me on LinkedIn, you can find me on Google+. It's fairly easy to find my information. So feel free to reach out to me and ask questions about the distribution or about working with RF. There's just a lot of fun